Hello, today we are going to start looking at section 11.2 where we will be comparing data sets. The learning target for the next couple of days is that I can use measures of center and spread to compare data sets. Today we're going to focus primarily on dot plots and box plots. Before we begin, we want to look at a couple of key vocab terms so that we understand what we're comparing. And the first thing that we're going to compare are the measures of center, which you learned about the other day. Examples of measures of center are the mean and the median. And depending on which type of model you're using will determine which of those you talk about. And the other thing that we can talk about is the measures of spread or variability. The two examples you've learned about are range, highest to lowest, and interquartile range, which you learned about when you learned about box plots, quartile 1 to quartile 3. Two things that you'll learn about in the future are standard deviation and variance. So you'll learn about those later this chapter. Okay, so again, our job today is to take a couple of sets of data and compare them. You can see example 1 is to compare two dot plots together. So when we look at this, it says Sawyer has narrowed his car search down to two different types of cars. To make an informed decision, he gathers data on estimated highway fuel efficiency, miles per gallon, of the two different types of cars. The dot plot shows the data for each type. Okay, so we can see that the top box plot represents the first type of car he was looking at, and the bottom dot plot is the second car he was looking at. And the question below we see is if fuel efficiency is the most important feature for Sawyer, which type of car should Sawyer purchase? So maybe pause the video real quick and just look at what you see and see if you can come up with a guess or an educated decision on what he should do. Okay, so now let's talk about some of the math behind it, using some of the vocabulary we've talked about. If I look at the top box plot, I can see that majority of the values fall kind of in this, what we'll call cluster, between 33 and 38 miles per gallon. Okay, so I would say that there's a lot of clustered data points in there. Then you have this one that's up at 41. 41 is pretty close to 38, so I would not necessarily consider that an outlier. So it would be there. Now we can see type 2 is a little more spread out between 35 and 44. The biggest, what I would consider cluster, I guess, is from 37 to 40. But again, there's still some fairly decent values up until 44. Okay, so the cluster would be considered higher than the cluster of type 1. The other thing I notice is that there is an outlier. The 51 is way off here up to the right. Okay, so when I look at these two things, I can see that I would think that type 2 would be a better option. Now, so just visually looking at the dot plot, that would be my best estimate, that I would want to go with type 2 because of those things. Having said that, the next slide asks us to do some math. Okay, so if we look at type 2, we are going to actually calculate the mean with the outlier, and we're going to calculate the mean without the outlier. So this is actually going to teach us how the outlier affects the mean. Okay, so if we go with type 2, remember to find the mean, I add up all the values. So if I was going to add up all the values, I would take this dot at 35 plus 36 plus 2 37s plus 2 38s plus 2 39s plus 2 40s plus 41 plus 42 plus 43 plus 44 plus 44 plus 51. Okay, when I added all of those up, so this is number 1, I got 644. Now there's 16 data points, so for this problem I did 644 divided by 16, and I got that with the outlier is 40.25 miles per gallon, if I include that 51. Okay, so I'm only going to show how I actually added all those up once, but then for number 2, calculate the mean without the outlier. This time I added them all up except for the 51, sorry. So when I added up all of them without the 51, I got 593, and again, it was one less piece of data, so it's divided by 15, and I got 39.5 miles per gallon. So you can see that if I take out that outlier, I actually have a smaller mean. So we can actually look at this and say, okay, how does the outlier affect the mean? Well, the outlier pulls the mean closer to the outlier because 40.25 is closer to 51 than 39.5. So the outlier pulls the mean towards it. Okay, so again, I could go back and calculate the mean of type 1 to see how the means compare, but everything else I looked at, I feel pretty confident that type 2 is my best bet. But a lot of times with the dot plots, we'll be focusing on mean as one of the measures to compare. Okay, so I want you just to take a minute and we'll read this problem and then I want you to think about it. It says a teacher feels that the students in her class after lunch are not paying attention. She plots the grades on the most recent test to examine the situation. What is the mean for each class? Can you conclude that her hypothesis is true based on this data? Okay, so go ahead and pause it. Calculate the mean for both so you can practice doing that and then see what you think. Okay, so hopefully when you went to find the mean, you added up 77 plus 86 plus 87 plus 88 plus 91 plus 93 plus 96 plus 97 and then divide by 1, 2, 3, 4, 5, 6, 7, 8. And when I did that, I got 89.8 is their average score, their mean score. And for the afternoon class, again, I added up those values and divided, and I got 89.3. So we want to know, again, she thinks that her afternoon class is more distracted and not paying attention. If that was the case, you would see significantly lower scores, or you would think you would. And if I compare 89.8 to 89.3, I just don't think there's a big enough difference to account for that. Okay, you could also look at how the dots are kind of organized within the plot, and you can see there's not much discrepancy. Okay, so the second thing we want to look at today is what if we have data that's represented in the box plots we learned about. Okay, and so we'll look at this first example of comparing data sets displayed in box plots. Caitlin and Philip go to neighboring high schools, and both are sponsoring charity fundraisers. Caitlin claims that students at her school are raising more for charity than students at Philip's school. So Caitlin thinks her school is winning. The amount raised by a random sample of 30 students at each school are shown in the box below. Do the data support Caitlin's claim? Now the question below is, do you think sample size is large enough to make this claim? If so, do the data support her claim? I think you could go either way on that. Usually 30, I mean, I suppose that's one full class if we think about Edina High School. Having said that, one class compared to the entire school may not be enough. But we're still going to proceed. Usually we'd maybe like to see our data, our sample size a little bit larger. Okay, but let's look at the data we do have. One thing that I noticed, so when we're talking about box plots, we always have a max and a min. Well, if we compare the max and the min, we can see that they are the exact same. So the range of the two is the same. Okay, so again, it's important to always think about these new math terms we're talking about. Okay, so the range is the same. So the range itself tells me nothing. Now, the nice thing about the box plot is that we can quickly see the median. Okay, so we're going to use median instead of mean when we're talking about box plots, when we're talking about the measures of center. Okay, so Caitlin's median looks like is 5 is 45, whereas Philip's median is 50. So if I was going to use just the median, I would say that Caitlin's claim is not true because Philip actually has a higher median. Now we do have to be careful because sometimes just the median isn't enough, okay? So another thing we learned about box plots is this thing called interquartile range. Now remember, it represents the middle 50%. Okay, so from quartile 1 to quartile 3, Caitlin goes from 32 to 52. So she's got an IQR of 20, so it's a fairly wide spread, but it's also at lower values than Philip's, which is actually pretty important. So Philip's interquartile range goes from 45 up to 56, it looks like. So he's got an IQR of 11, which means that he actually has a smaller interquartile range, so less variability, but that less variability, the 50% of his sample size, is at higher numbers than Caitlin's. So it's for all of these reasons that I would argue that Philip's school actually did a better job of raising money. And those are some different things we can look at with box plots. Just a couple last examples that you can look at just to continue to think about what you can look at in these types of box plots. Here's another example. Kaylee is working on a project investigating the number of music downloads students in different grade levels performed the previous week. Kaylee thinks 9th graders download more music than 11th or 12th graders. Is Kaylee's claim supported by the data? Why or why not? So she's not even looking at 10th and 11th. We could go back and talk about that. But she thinks that 9th graders produce more. Now, if I look at this, just a quick glance, number of downloads, the quartile 3, so the top of the 50%, remember this is 50% of students fall within that box. The most of those 50% of students is 5 downloads, whereas that's the bottom end, so quartile 1 of 12th grade. So we can clearly see that the 50% of students falls above the same line that the other falls below. So 12th grade would actually be downloading way more. One last example to look at, making observations. Provide a possible explanation for each of the observations listed down here made about Nadia's data about her classmates' texting habits. So we can see that we're looking at average numbers of texts sent on a school day versus a non-school day, which is very interesting. Okay, so I want you to read the 3 observations, pause the video, and see if you can think of an idea for each. So when I read students send far more text on non-school days than on school days, I could use multiple things to support that. Okay, I'm going to focus on the box, and it goes from 40 to 60. So the entire 50% falls way higher than the entire 50% of non-school days. Okay, so we can see that way more students, it appears, send text messages on non-school days. The second one says there's more variation in the number of texts sent on non-school days than on school days. The minimum of both is 0, but the maximum is 26. So there's a range of 26 texts sent on school days, whereas the maximum here is 80. So there's a maximum of 80. So a much bigger range and a bigger interquartile range if we just did that. And then it says, one person did not send any text on non-school days. This represents an outlier because it is far from the other data values. That one's a little harder because we don't have the dot plot showing what's happening in between here. However, since we know that 50%, and actually this line right here would represent another 25%. So 25% of students fall between 0 and 40. We could maybe anticipate that 0 could be an outlier. It would be hard to know for sure if there's a cluster down there. There could be a whole cluster of students down here, but it is pretty far away from the 40. So I think that's actually a fairly decent claim. Okay, so those are just a bunch of examples. You can see on this final slide, I made a note sheet of just some key things, the objective, some vocab, and then one example of a dot plot and one example of a box plot. So hopefully you enjoyed watching the video and you were able to just follow along, but I would make sure I get some notes down so that you have that for reference. Your homework tonight is 11-2A in Pearson. And don't forget to fill out either your Schoology or Google quiz that your teacher put up for you for your ABA for today. Thanks.